emulators, like let me quit this one and use the other version because I think this is more like what you guys see, particularly on the PCs. So you want to go to, let's see, where is it? Drive, attach disk image to drive 8, and then go to the directory where it is, which in my case, GitHub, CS371, manuals, program reference, and then I can go back and then I can load. Here, let's do Control-2. Oops, that doesn't work in this version. So that's if you use that version of the emulator. I prefer personally the GTK version. It just works a little better for the most part. All right, so then we want to, in this version, attach disk image, drive 8. If you've already attached it before, it will have sort of recently things that you have attached, but otherwise just select the file and then attach or load. And then we want to load page 110 in this case from drive 8. Okay. Did you guys hear the disk drive? Yeah. Yeah. Okay. So, yeah, that's what that was. Okay. So let's go back to page 110. I wanted to kind of revisit a little bit, talk in a little bit more detail as to where we were before. And it was this program here. So let me list it. Okay. Which it's a little easier to read on the screen here, but let's just sort of talk through what each line is doing. Okay. So the first one here, print character 142. Let's just do that line by itself. Okay, you'll notice that there was no change here. So it's possible to, and I don't remember which character code it is. The character set has both graphics for upper and lowercase. And by default, it defaults to uppercase, but you can change it to to use the lowercase version instead. And all that does there is changes it back to the uppercase if it had been changed to lowercase. We didn't notice any effect from that because we were already in uppercase mode. Okay. Yeah, so one of the limitations of this machine in many respects is that you really can only display one version at a time in a lot of cases, which meant that, like, for something like word processing, it was a little janky. But yeah, okay. So then the thing that we're going to do here, so you see we're poking two memory addresses, 52 and 56 with some values. Okay. So the thing that we want to look at and kind of understand in a little bit more detail is what is the memory map? Like, how do we know what memory address 52 is? Okay. And what, so how do we know where in memory things need to go? Well, we basically just have to read the manual. And there is a list, although I'll show you, it's probably easiest on the C64 wiki to look at it there. Yeah, we'll just pull it up from there. That's probably a little easier. Oops. All right, so let me find what exactly I'm looking for. And then Okay, so here is the one of the pages on the C64 is for the memory map. Okay, um, so the and we've talked about this a little bit about things being sort of banked in and out, but here's the default overview as to where everything goes into memory. So you have uh, RAM starting here at the bottom, okay, and the different boxes are what's going to get mapped in depending on whether or not there's a cartridge in the system or not, okay. And for example, basic ROM will be loaded into this range of memory if when the system is powered on. Also, the kernel is loaded in, character ROM and IO. So this is how you get to the different chips or whatever, the VIC2 chips, that's for graphics. So all of the internal registers are handled for in these different locations. And so, for example, what was the memory address we were poking here? 52. All right, so that particular memory address, um, 52 is on the 0 page, okay? And the 0 page is the bottom. Um, so on the 6502 processor, it could address 64K of memory. And the way you think about it is that each page of memory is 256 bytes, and you have 256 of those pages. So you can think of it like the memory is like a big book. Each page is a grid of 256 memory addresses, and they're arranged sort of in the order like a book would be. Okay. Now, the 0 page, so this will be the very beginning of the memory address space, was special in the sense that you could access that memory slightly faster than you could all the other memory locations. And when we get into assembly, I'll explain why that was possible. Okay, so the 0 page got used for, you can almost think of it like a bank of 256 different registers. Okay, because it was faster to access it than the rest of RAM, programmers would use that stack or the space on page 0 as sort of a good location for temporary values because you could get to them fast. But they would also be used by, in our case, the system. Some of those values are reserved for certain things. Okay, so for example, address 0 and 1, okay, basically allow the configuration on which direction, well, they go together, but basically you get to set whether or not you've got input or output on certain devices, and then address 1, if you change which you change values of some of those bits, then you can basically turn on or off whether or not you're using ROM or RAM in certain places, right? So this is where you actually write to change the values or to tell the PLA to reconfigure the railroad tracks, okay, using our analogy. Is that okay? So what was the address that we were looking at? 50, was it 56, 52? Well, let's just go back because I don't remember. Uh, 52. Okay. So let's go down and see what is byte number 52. Okay. So let's see. It is high byte of free top, the top of the string stack. Okay, that's not particularly enlightening. It was 52, wasn't it? 50. Oh, and also 56 while we were at it. Okay, and highest basic RAM address and bottom of string stack. Okay, So I think basically what we're doing there is we need to basically tell, and we're poking in our cases the two high bytes, to basically allocate memory, or basically tell BASIC that, hey, you can't use certain memory addresses. We're going to change where is free for RAM and where's not free. Okay, so that's that print or poke. Okay, great. And then line 20, I already mentioned last time, which is 56334. Okay, so let's look at that one, which isn't on this page, obviously. So we need to go down to, what was it, 56? So that would be, where is that? Well, okay, so 56, what was it, 56334? What's it? Sorry. 56334. Okay. So, okay. Yeah, because I have to say where I'm poking and what I'm poking it with. So poke 52 means I'm poking memory address 52. Okay, which is whatever that was in hex. And then 48 is the value I'm putting in that byte of memory. And in this particular case, we're poking both of them with 48, which in hex, what is 48, by the way, in hex? 30, right, as a single byte, okay. Yeah, so you have to say where are you poking and what are you poking there. Okay, this one, 56334, the comment tells us it tells off the key scan interrupt timer, okay, and 56334 would be in this range, okay, which doesn't have a link to it, but we can do, let's just search for the key scan and see where that is, or let's do keyboard, keyboard. Direct addressing, keyboarding, peek and poke. Okay, well, I'll find it, but basically, I mean, it already tells us what it does. It just turns off the routine of the kernel that sits there waiting for checking has a key been pressed, and by doing so, our program will run faster, is essentially it. And in fact, we can actually demonstrate that. So why don't we just run it, and let's just measure how long it takes. So somebody get out a phone. Well, here, I'll just use mine. And let's run a stopwatch on it and see how long it takes to run this program. All right, so stopwatch. Okay, ready? Okay, basically 9 seconds. Okay, and then if I remove lines 20 and also line 60. Okay, so I'm no longer turning off or on the keyboard routine. I'm just leaving it on the whole time. Then if I run it, so we're already well past what we were before. Okay, we're more than triple the runtime from before. Can we get the idea? Okay, I don't actually care how long it takes. The point being, it's way longer than it was before, and I'm going to have to reset this to do that. Okay, so Control 2. Okay, now we're back to where we were before. Okay, so let me rerun it. Well, actually, before we do that, let's keep talking about what it's doing, right? So we're changing the key scan, turning off the key scan, and then here in our loop, right, what are we doing? We're copying stuff from the graphics memory to a different location in memory, okay? And all that's doing is copying data from one place to another. That's not particularly exciting. And in assembly, or excuse me, in BASIC, how you do this is you have to peek to get the value in the old address and poke that to the new address. Okay, so nothing particularly exciting. You're just peeking and poking, but you're doing it a single byte at a time. In assembly, you would do this actually with two machine instructions. Load A, or load the accumulator, basically load the register with the contents of memory, and then store it to this other location. That's it. Okay. Okay, so that's just copying stuff. All right, now, where we really want to pay attention is the next line. Okay, so line 50, what is that doing? Yeah, sort of. Okay, but we're changing the value of memory address 1. Okay, how are we changing it? Well, what is peak 1 going to give me? Peak of 1. What will that tell me? Like, not the specific number, but what information? Yeah, I'm going to get whatever's in memory address 1. If I OR that against the number 4, what is it going to do? All right, so we have to think in binary for a minute. What is 4 in binary? Yeah, from the right, there'd be a 0 in the 1's place, a 0 in the 2's place, a 1 in the 4's place, and zeros in the other 5 bits. Okay, so what this will do is change the second bit from whatever it is to a 1. It maybe was already a 1, who knows? Okay, does that make sense? Okay, now, what's so special about memory address 1? Okay, let's go back to the wiki, to the memory map. Okay, and we wanted to go to page 0. All right, so memory address 1, bit 2. Yeah, so what is that doing? Okay, configures IO or ROM at D00 through DFFF. Okay, and so we have, by switching bit 2 to a 1, it's changed, well, just that bit. Okay, and then we'll look at the bank switching here in a minute to get more details. Okay, so when we peaked, we're getting whatever those bits currently were. And then we OR against 4 to switch the bit that we want, but leave all the others the way that they already were. Does that make sense? Okay, now why is it a good thing to leave the other bits the way that they were? Well, what do the other bits do? They deal with other things, right? And we don't want to mess with them. So if we want to change a specific bit, this is the trick you have to pull. You can't write a single bit to memory. So what do you have to do? You can only write a byte. So if you want to write a byte to switch a specific bit but not mess with any of the others, you OR against the bit pattern that you want, and that way you preserve what's already there. Does that make sense? Okay. Because you'll notice that we're going to use tricks like that quite often, at least in BASIC. Okay. Now, and then when we get into this in assembly, it'll be essentially the same kind of trick. Okay. Is that okay? Okay. So this is configuring whether or not we have IO or ROM at this particular address. okay? And so let's look at the bank switching, okay? And um, so we just changed the basically this chunk worth of memory, right? And we have changed it to be a 1, which means that what is in that page is now input-output rather than what it was before when it's a 0, which is um, the character ROM, okay? So, or sorry, not input-output. We've changed it. Well, actually, let's poke and see. Um, let's peek address 1, well, print peek. Okay, so 55. Okay, so does that make sense? 55, what is 55 in binary? Okay, so let me just write this out. Bit, okay, so bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, and bit 6 and 7 are undefined, so we can ignore those. So what is bit 0? That's definitely a 1, right? Because we have an odd number. Okay, so what did you say it was, Artie? Okay, so that means we've got 1, 1, 1, 0, 1, 1. And these correspond to bit 0 is low RAM, bit 1 is high RAM, bit 2 is car RAM, bits 3, 4, and 5 all have to do with the cassette data line, which we can ignore because we don't have a cassette plugged into the machine. Um, yeah, okay. So, and so that would be cassette motor off, uh, cassette switch is closed, and then bit 3 is that there's a date, right? So none of those, we can ignore those 3 because I don't have a cassette plugged into the machine. Okay, so if we go back to um, the bank switching part, right, then what have we done? Our CPU control lines are actually, they're all 1s in this case, okay? So what do we have in memory now? We have, instead of having the character ROM here, we now have changed it to IO, okay? Great. And so what this has done is the character ROM is no longer located there. And we have one more address to poke, which let's go back to the manual. Um, okay, so what else did we have to do? We had to do this line, right? Nothing happens. Okay, so what do we poke when we poke 53272? So where is that? It's on this page. Let's go back to the memory map. 53272, which would be on here. Okay, so these pages. All right, 53272 is memory pointers. Okay, so we're basically going to tell the machine, right, go look over here now for where you're going to get your character art instead of where you were looking before. Okay, so if we look at, we've run the program, right? Or did I run it? No. Okay, so nothing changes, right? So what do I have to do to actually notice a change? Well, before I do anything, let me do this poke. So let's poke 53272 with the result of peaking 53272 and 240 plus 12. Okay, so what changed? Not quite. So far, all that's changed is the way the cursor looks, right? Okay, and the reason is because where it's going to get the cursor graphics is different than it was before. And it just so happens that the cursor graphics where it is now look different than the sort of default did. Okay, but watch this. So let's do this thing here, right? And so I'm going to run a for I equals 122882, 12288, and I'm actually going to do 512 plus that, or let me do 511. Poke I with 255 minus peak, oops, peak of I. All right, so now watch as this happens. Nothing happened. Oh, yeah, thank you. Cool. Okay, so what did I just do? I did mess with the screen, okay, but what I was really messing with was where the characters were, the art for the characters was stored in memory, okay? So the book, it says for I equals 12288 to 12288 plus 7. That's only going to do how many bytes worth? 8, right? And if I had messed with just those, it would have reversed the first symbol in the table, which is the at symbol. Okay, so I did that, and you guys saw how for each character it was messing with, it did it one it took 8 iterations before the character was fully reversed, right? And in fact, if I run this again, it'll re-reverse them. So let's do it again. So watch it again. Right? So you see how it was doing the top of the, so this is the order it would do it in. The at symbol, top row, next row, next row, next row, next row until it's done. And then it moves on to address blah, blah, blah plus 8, which is the top row of the A, then the next row of the A, the next row of the A, and so on. And then it does the B, and then the C, and then the D. And so you guys saw how it was scrolling in basically as it was reversing each letter. Yeah. Okay. And in this case, we've gone through and reversed. So how many bytes have I messed with here? By going from here to here plus 511, how many total bytes have I messed with? 512 bytes, yes? Okay. How many characters, therefore, have I messed with? Well, okay, how are we going to answer that question? What information do we need to answer that question? How many bytes there we need per character, right? And how many is it? It's 8, right? Because each character is an 8 by 8 thing of pixels, and all we're doing is turning them each pixel on or off. So it's 8 by 8 bits. 64 bits is 8 bytes. Okay, so if I mess with 512 bytes and each character takes up 8 bytes, how many actual characters have I messed with? Yeah, 512 divided by 8 is, last time I checked, 64. Okay. Um, Now, we could have messed with more of them, um, except what would be so in this example, they only copy 64 bytes worth over. Why would we maybe want to copy more over? or not copy that over? Well, what else is in the character memory, right? There's all those weird symbols and things that we can make like boxes and art with. Do we necessarily need those? No, so if we don't need them, don't copy them, okay? The other thing would be, well, what would happen if we did copy them because we did need them? What would be true about this program? So let's say I copied more data. What would that take? Yeah, I need to allocate more memory, but also it would take longer to run. Yeah, makes sense? Okay, so don't run longer than you need to if you don't need it. Okay, question? Yes. Yeah, there is. Yeah, okay. So why, and that's not actually stored as part of the character art. Okay. So in the character, so for example, right, we saw this last time when we started messing with how the ampersand looked. A 0 means that that pixel is going to be drawn with the background color. And a 1 means it's going to be drawn with the foreground color for that cell, okay, which is defined in color memory. And this is why I could change the colors of each letter individually, okay, but I can't change the background color for each one individually. I can only have one background color, okay. And for that matter, where is the background color stored? Okay, and I don't remember the address off the top of my head, so let's look at the reference. Okay, um, so it's actually stored there in 53281. Okay, and so let's change 53281 uh, to something. Okay, so I would poke 53281 with, well, let's change it to 0. Okay, color 0 is black. Color 1 is, well, that was a bad decision. Okay, because now I can't see anything. All right, so 532, what was it, 28281 with, let's go with color number 2. Okay. Yeah, so let's go back and rerun this, right? Uh, that's pretty cool. But look at our background. Well, okay, so now why are the characters like this? So why does the screen look like this? Because essentially I've reversed background and foreground. Okay, so let me rerun the program to get it back to the way it was. Okay, so it didn't look like I had multiple colors of background. What I actually had was multiple colors of foreground because I had reversed what background and foreground was for the letters, right? That's an interesting trick. Yeah? Okay. So yeah, so we can mess with that. And also you see the blue border around the outside? You can also change it, okay? And it's in 53280. So let's change it to something. Let's do color number 12. How about that? That's gray. Yay? Okay, so back to our program. Oops. All right, all this program is doing is copying the character definitions from the 64 bytes worth of it from the ROM into RAM. Okay, um, and but we noticed something about the cursor. What about if we copy more data? Let's copy 128 bytes instead. So what do I need to change in this program? Instead of for I equals 0 to 511, what should I change that to? Let's just double it. So it'd be 1023 now, right? Okay, so to 1023, poke I plus 12288 with the value of peak of I plus, what was it before? Here, let's get the manual open. 53248. Oops. 53248 colon next. Okay, good. Okay, so what have I done? I've just changed it, so now it's going to copy double the amount of data. Okay. Now, do we really need to copy the first 64 bytes again? No. Okay. And actually, I should have reset it before we did this because we already, by doing this instruction here, but no, actually, this should still work. Let's see what happens when it finishes. Well, okay. So the cursor stayed the same, but if I printed, for example, let's print, oh, I don't know. Let's just print some characters. Oh, yeah, by the way, some of the characters, if you print them, they change the colors, right? Which is kind of neat. Okay. That's a pi, right? The mathematical pi. Oops, missing a, uh, right? Cool. Yeah. Okay. So when you read code like this, you look at it and it's not entirely clear what these memory addresses are. This is why you would have both your reference manual and back in the day, of course, lots of other books. Now, of course, we've got this wiki, which is nice. Okay. All right. Let me reset this back to um, normal, and then I want to revisit um, we'll come back to multicolor mode later, but essentially what you can do is you can actually have multicolor characters um, at the expense of horizontal resolution. So if you ditch half of the horizontal resolution, you can now use two colors, which is okay, fine. So for example, here, this is how it splits. And for letters, that might be pretty good. But for trying to do art, it kind of still looks a little janky. Okay. All right. So we'll come back to that later. But let me go to the sign routine. Okay. And so let's load off of the disk. Okay. This and look at what else is going on here. So we're now in the bitmap section. Okay. So, in order to draw an entire screen worth, okay, it requires 8,000 bytes worth of memory. Okay, now why 8,000? What's the size of the screen? Okay, and when I say the screen, I mean not the border part, but the rest of it. It's 320 by 240, or sorry, 320 by 200, okay, which multiplies out to 64,000 different pixels. Each pixel requires 1 bit, and hence 8,000 bytes are needed to store it. Okay. Now, how much is that relative to how much memory we have on our machine? How much memory do we have on our machine? 64K, and we're using 8K basically for the screen. So it takes up an entire eighth of the system memory just to draw the screen part. to keep track of what's on the screen. That's not to mention the color memory, which takes up another chunk, okay, and then, other things. So we don't really have all 64K available, even if we, well, okay, actually, I take that back. So there are some programs, for example, one that I've used, a disk copy program. If I want to copy one disk to another, right, you can think of that as basically being like what we just did in our other program. We're loading from one piece of memory and putting it to another piece of memory, except this time the source and the destination are both floppy disks. Okay, you can imagine that that's a pretty slow process. Yeah. Um, and would it be helpful to have lots of memory to do that? And so some of the programs, like a disk copy utility, will temporarily turn off using the screen, and it will use the screen memory as more RAM. And so while it's copying, your screen is just going nuts, right? But it therefore has more memory, and so the copy happens a little faster. But yeah, and maybe I'll show you guys that eventually. Okay, so let's talk about how this actual sign routine works, okay? And this one is plotting sign, but what it's doing really is bitmapped graphics, okay? So it's going to change the control of the graphics to, instead of displaying characters, to display using, thinking about manipulating individual bits of the character memory, okay? So looking through each line here, all right, base equals 2 times 4096. That's just defining a variable, okay? No big deal. What are we doing with address 53272? Well, what does address 53272 do? Have we used that one before? Okay, so let's go back to the reference, right? What is that 53272? Oh, sorry. Memory pointers, okay? So we've used that before, right? When we basically said, where in memory are you going to go for to access graphic stuff, okay? And we are poking it with the result of what it currently is, or 8. So that means we're switching the 8th place bit of it, which is 1's place, 2's place, 4's place, 8's place. We're changing this bit right there. Okay, great. What else do we need to do? Poke 53265 with its current value, or 32. So where's 53265? That is control register 1, and we're changing the 1, so 1, 2, 4, 8, 16, 32. We're changing this bit, whatever that does. Okay, and I'll have to go dig through more manuals to see what BMM means. Okay, but it's a control register, and so this has something to do with the controlling the graphics. Okay, all right, great. Now what? For I equals base to base plus 7999, poke I comma 0 next. Okay, so what did that do? This is going to change 8K worth of memory locations to all be what? All to have value what? They're going to change them all to be 0, right? It's going to zero out every single one of them. Okay, how do I know that? Because I'm poking each one with the constant 0. Okay, then what am I changing for from 1024 to 2023? How many addresses is that, by the way? Yeah, 1,000, right? And guess where that 1,000 came from? Well, that's color memory, right? So the color memory, is how many characters can be on this screen at any given time? How wide is it in terms of the number of characters? It's only 40 by 25. Okay, and guess what 40 times 25 is? Almost just 1,000, right? Which is why this line goes from 1024 to 2023. How many things have we done there? Just exactly 1,000. Okay, so what am I doing? I'm changing all of those memory addresses to have the number 3 in them. Okay, well, if I poke, for example, 1024 with 3, okay, what happens? What happened to the top left of the screen? Okay, so it's not color memory, it's character memory. It changed it to a C, right? So it's going to change which character is being displayed in each of those grids. So if I were to run this loop, that's just the loop on line 30, what would happen to every single character on this screen? They would all become C. Okay. Now, is that particularly useful? Not really. Okay. But it is if I redefine what C looks like to be like blank or something, right? So I could use this to kind of wipe the screen. Okay, then the pixel part happens. Okay, so if we ignore, like if I basically ignored lines 20 and 30, right, then all it's going to do is kind of wipe the screen. All right, so let's run it and let's watch and we'll see exactly when line 20 is happening and exactly when line 30 is happening. It's very obvious when they are. Okay, good? Yeah? All right, so run. All right, line 20 is currently happening. And what that is doing is zeroing out 3 or 8K worth of memory. Okay, and then that's line 30. Okay, and now it's doing the sign plotting routine. Okay, so we'll let it do, well, actually, let me quit it because I'm going to need to reset so we can go back and look more at the code. Okay, so let me reset it. Okay, so then what's happening from there? Okay, is the so lines 50 through 120, okay, are all the plotting part here. Okay, so I'm going to basically divide my x-axis into, well, it goes from 0 to 319.5, 320, right? And I'm going to divide it into 0.5 increments. Okay, is that all right? And so basically I'm going to compute, well, 640 values and try and use those to plot. So for a given x, I'm going to compute the y value that goes with it, and then I need to figure out what to change in screen memory so that I can actually see the plot of it. Does that make sense? Okay, so the first thing is line 60. That's the function I want to plot. 90 plus 80 sine of x over 10. Okay, and I can change that to be something else, obviously. Good? Okay, so the sine function is built into BASIC, and so part of BASIC, there's some code someplace that actually computes the sine of an angle. And we can even find that code if we really are curious as to how it does it. Yeah? Okay. All right. So once we've got that, what else do we have to do to that number? It makes it an integer, right? So you see it says int of blah, blah, blah. What is that going to do? It's going to round that number to an integer. And why do we need to do that? Yeah, because all of the coordinates, every pixel on the screen is an integer, comma, another integer, right? An X and a Y location. So I have to round it because I can't, what does the 12.5th pixel mean? That doesn't make any sense, right? I'm either going to mess with pixel 12 or pixel 13. Can't do a half pixel. Okay, so that's why it's going to make it an integer. All right, now the next three lines are the kind of weird part, and I'll go back to the manual in a moment. Okay, I need to compute basically which character, which row, and which line am I on, so I know where in memory to go. And those formulas, I'll show you where they come from in just a second, okay? And then the line 90 is where they get put together. Basically, how do I know where to change, what memory address to change to plot the dot that I just computed? Does that make sense? Okay, so let's look at the manual so we can see what that formula is. Okay, so the manual for bitmap mode is okay, here's how it's actually arranged. Okay, so how many bytes did we say it takes to draw the whole screen? Okay, it was 8,000 of them, right? Okay, the top row, okay, is going to take, or the top line is going to take this many bytes, okay? So that's the top, I'm dividing my my screen here into 25 rows, each of which is 8 pixels tall. Okay, so for the very top row here, where the line that has ready, I need 1 byte to store everything for where the R is, 1 byte for where the E is, and so on. Okay, and so how many bytes total is that going to be? Or sorry, not 1 byte, it's actually 8 bytes, sorry. It's, where is the R? Okay, how many bytes does that take? It takes 8, and those are bytes 0 through 7. So 0 through 7 is where the R is. Okay, where's the E? 8 through 15, 16 through whatever, and so on. Okay, and then I get all the way over here, and the very bottom end of that last little block is byte number 319. Okay, so that's the first row of 25 slots. And how many more, 40 slots. How many more are there? 24 more of them, right? Because it's 40, 320 pixels each of, and we're subdividing into sort of 8 by 8 grids. Okay. All right. So is that okay? Just the idea. Okay. So if I have a particular location on the screen that I want to plot something to, in terms of its pixel number, I have to know, I need to determine which byte am I actually going to go to, right? Well, okay, so if I know my y coordinate, right, I need to know, therefore, which row is it in and which line is it in, or, right, and which character spot is it in. Is that okay? All right, so that's sort of the problem. And here is the computation. So which row I'm in is, I take my y coordinate and I divide it by 8. Okay, why? Because how many rows are there? Or sorry, how many bytes does it take per line? Okay, it takes 320 bytes per entire line, okay? And so the row number is going to be a number that's between 0 and 24, okay? And what's the maximum that our Y number could be, theoretically? Well, what's the size of the screen? Hmm? Well, that's the total number of bits that it would take to, or bytes, sorry, to describe it. But yeah, the largest Y value that you could have and still be on the screen is 200, right? Because the screen's 320 by 200, right? So if we compute a Y value that's bigger, then what does that mean? We're off the screen, and so you can't draw it if it's off the screen. Sorry. Okay. All right. So what that means then is our computation here for our function, we had better be sure that it doesn't ever exceed 240, and does it in this case? What's the biggest number that we ever get out of that function? Yeah, so line 60, sorry. What's the biggest value that that can ever be? 170, right? Because sine is always between -1 and 1. And so at minimum, it will be 10, and at maximum, it'll be 170, right? So if we were stupid and changed that 80 to like 200, it would work for some of the pixels, but we'd get an error because we try to access things that aren't screen memory because we'd be running off the screen. Okay, so is that okay? The row number. Yes? Okay, so if I divide 200, the maximum number, well, it actually would be 199, right? Because 0 is a row number. Then the biggest I'm ever going to get is 24. Yeah? Okay, meaning rows 0 through 24, there are 25 rows. Yes? Okay, now the character, right, is x divided by 8, right? So what this is doing, right, is I'm determining, so you can think of character actually as being like a column. So how many characters wide is my screen? 40, right? Is that okay? So by dividing by 8, right, it's because there's 8 bytes per character, right? I'm going to get basically which row and which column my pixel lives in. Yes? Okay, but that only narrows me down to how many bytes? How many bytes would has this narrowed us down to? 8. Okay, why 8? So I've subdivided my screen into 8 by 8, an 8 by 8, or sorry, 8 by 8 units. There are 40 of them wide and 25 tall. This has now told me which of those grids I'm in. But the grid is still an 8 by 8 thing. So do I know which byte I'm in yet? No. Okay. So line is Y and 7. Okay. And let's think about what that's doing. The character position, okay, from 0 to 7, if I and it against 7, what am I doing to the number Y? I'm stripping out its lowest 4 bits. Yeah? Okay. So now I know which, or sorry, not 4 bits, 3 bits, because I'm stripping out, I'm preserving the 1s, 2s, and 4s place. That adds up to 7. And then all the other bits are going to get zeroed. Okay, so how many positions is that? A total of 8 of them, 3 bits. Okay, so the number line here will be something from 0 to 7. Okay, and that will tell me within, so let me sketch this, within the 8 by 8 grid, okay, am I in the first line, second, third, fourth, or down at the bottom one? Okay, so I've narrowed it down to which byte I'm in. right? Because the first line is the first byte, the second's the second, and so on. Yeah? Okay, but do I know which bit I need to be in yet? Not quite, and that's on the next page. Okay, it's this. Okay, so x against 7, and then I subtract that from 7, and the let's think about why that should be the case. So if I and it against 7, what's that going to do to x? It's going to give me its lowest 3 bits, right? And if I subtract that from 7, then let's see, why is that the case? Yeah, it sort of flips it, but let's think about why we should do that. Um, yeah, so x and 7 is going to return a number from 0 to 7, right? And if we subtract that from 7, we'll get a number from 7 to 0 instead of from 0 to 7. It just flips it. Why do we do that? Oh, I know. Because where's bit 0? It's on the right, not the left. Yeah? Okay, because when we write down binary numbers, what do we write down first? The largest value, not the smallest value. Okay, so the smallest value is on the right, and the lowest value, or the largest value, is on the left. We're writing the big end first. Yeah, so that's why we have to do it, because of the endianness. Did you guys know that, by the way? I think I mentioned it before. The word endian, Endian. So it's which order you store your numbers. Do you store the most significant bit first or the least significant bit first? Right? There's two ways to do it. You just have to choose something. Okay. And then why is it called endian, Endian? Well, it's which end do you put the big number on? Kind of makes sense, but it's actually better than that. Does anybody know really where it comes from? No? How many of you guys have read Gulliver's Travels? This is your hashtag liberal arts college moment for the day. No? None of you have read Gulliver's Travels? Not a single one of you? Doesn't count. Okay. So there's an island, right, that he goes to, and it's divided into two factions. Okay, the big Indians and the little Indians, and it's which end of the egg do they crack? The big end or the little end? Yeah? And they go to war over it, right? I mean, it's a huge thing, and right, it just shows you that humans will divide themselves into two opposing groups over basically anything, right? Anything, no matter how insignificant and trivial, including which end of an egg do you crack, the big end or the little end? Yeah. Well, yeah, I guess, right? I mean, it depends on why you're trying to crack your eggs. But I mean, think of this as sort of like the, you know, 18th century precursor to the star-bellied Sneetches or something like that. Have you guys all read that one? No? Yeah, star-bellied Sneetches, Dr. Seuss. Yeah. Okay. Um, anyway, see, it used to be the case that people that studied computers were actually well read, and right, and so the when this sort of issue came up, hey, we need a term to describe which end we put the big end of the number on and which one we put the small number on, whoever came up with it was like, oh, well, it's like the big and little Indians in Gulliver's Travels. Let's just use that. That's funny. And they did. But now nobody understands this because nobody's read the damn book. It is a teaching moment. Okay. So next assignment or next class, there will be a quiz over Gulliver's Travels. How about that? Okay. Yeah, you'll take the L on that one. Okay. Fair enough. Multiple choice in one of my classes? Are you insane? No. Okay. So that computes which bit we need to be in. Okay. And then the byte that we need to be in is basically a combination of that, right? Using that formula. Row times 320, line plus character times 8 plus row times 320 plus the base, which is just where in memory this whole thing starts. Okay. And that will tell me which byte I need to go to. And this tells me how I need to poke it. Okay. So in our program, by computes the byte, right, according to that formula. Bi computes the bit. And then what am I going to do? How do I know which bit to flip? Right? So one of that bit value is a number from 0 to 7. Right? And 2 to that value is going to be what? What is that going to do? Yeah, it's going to basically do bit shifting, right? So 2 to the 7 is the biggest one you can get. And what is 2 to the 7th? 255. Or no, I'm sorry. That's a little high. It's 128, right? Because 2 to the first is 2. So 0, 2 to the 0 is 1, 2, 4, 8, 16, 32, 64. My bad. I can't count today. Okay. So it'll move something into the 64's place, and then by ORing against that, what was already in that byte, I'm going to flip just one of the bytes. I'm going to leave all of them the way they were, except the one that I'm flipping to be a 1, and that's where a dot is going to appear on the screen. Does that make sense? Okay. And that's all I have to do. And then just keep repeating this for, for however many iterations. Okay, so does that make sense? You know what? That's an interesting. Oh, what will that put this program into? That was actually deliberate. It's not a typo. Yeah, it'll never end, and hence, like the graph will just stay on there on the screen until you hit either on the emulator, you hit the escape key to terminate execution, or on the real Commodore, you hit the run stop key. Okay, so that just keeps the thing on the screen without moving the program. Okay, yeah, Patrick? Mm-hmm. Well, this is why you save it, right? Uh, Return to basic. Well, okay, if I hit escape, it will terminate program execution, but I won't really be able to type anything, or rather, I won't be able to see what I'm typing because what did the first chunks of the program do? They cleared out all the characters so that I can't type anymore, right? I could type, but I'm not going to be able to see it. So if you can type the right numbers to turn everything back on from muscle memory, then maybe you could actually continue to use it. But otherwise, you have to just reset the machine. Okay. Which, by the way, and this is really annoying back in the day, how do you reset an actual Commodore? You turn it off and you turn it back on. Okay. That's how you do a hard reset. There is a way to do a soft reset, but it requires a keyboard command or modifying the system to actually put a button in and wire it on. There was no hardware reset button on this machine. On later machines like the Commodore 128, I think, they finally included one because everybody and their mother was like, why would you build a computer without a hardware reset button? Okay. All right. So if I run this, let's think about what it's doing, right? And let's just watch it. And that will be our conclusion for today. Okay, so it's going through and clearing everything. We had messed with, because I did a soft reset, it didn't clear out what was in memory from beforehand. And so that's why there's still some of those dots on the screen. So it's now clearing everything back out. It's going to turn the screen background to that light blue color again. And then it will replot the function. Okay, so that's line 30, I think it was. Okay, and then now it's replotting the function. Okay, and yeah, not too hard, right? No, pretty cool. Yeah, I know it's not super easy either, but so what would be a really cool assignment for your professor to give you here? Well, okay, cosine would be, that would be a really lame assignment, okay? Well, if we can graph trig functions, what about straight lines? Well, okay, so the x-axis would be easy because you could just graph y equals 0 for constant values from x from 0 to 319, right? To do a vertical line, well, what's the y-axis? You hold x equals 0 and have y range from 0 to 200 or to 199, I guess, right? So I will post the fun and exciting assignment, which will be to make it be able to draw a line from one point to another. Okay? All right, good? All right, and I will see you guys next time, and we'll talk about data statements and maybe start talking about the sound chip and so on. So let's quit the stream.